First, let's talk about the integral test. So today we'll cover 3 of them. The first one is the integral test. Today, if you're trying to work out the infinite series, let's say the infinite series going from 1 to infinity of an, what you have to do is just go ahead and change it to its corresponding improper integral. So we'll just go from 1 to infinity, right? Match the numbers, and then we have the function version of this. Let me tell you, this and that either they both converge or both diverge. And that's actually good news because we should be slightly more familiar with improper integrals, right? So the deal is that if you want to determine if this converges or not, just go ahead and check the corresponding improper integral. That's the idea. However, there are a few details that we have to include. So here's the deal. First thing is that we have to make sure that the function, when you plug in n, gives you the an. So this right here shows you the connection between this and that. And just a real quick example, suppose you have a function f of x is equal to, let's say, x over 1 plus x squared. Then f of n, this looks like we have n over 1 plus n squared, and we want this to be the an. So this is the notation. That means that if you plug in the positive whole numbers, you get the an, all right? So that's that. That shows the connection between an and f of x. And you also have to make sure that f is 3, 6. The first thing is it has to be positive, meaning that it has to be above the x-axis. And then we have to make sure that the function is continuous, no gap, no nothing, all right? And then lastly, the function should be decreasing. So if you look at the graph, the function should be decreasing. And usually I'll just let my students to provide a graph. Usually that will be how to show it. Because if you want to show all this mathematically, it will take some time. So for my students, you guys can do that. But if you're taking a class that if your professor wants you to show slightly more detail, then just go ahead and just show whichever the things that your professor wants you to show. All right, anyway though. Next, we have the direct comparison test. Here's the deal. This right here, the infinite series as n goes from 1 to infinity of an. This right here, you will know it converges if you can show that this series is less than or equal to a convergent series that you already know. So I will just put this down as less than or equal to a known convergent series. All right, and we do have a small thing to mention. Right here for the an, we have to make sure that an are positive. So I will just write this down right here for you guys. With that being said, there's no way for us to end up with like negative infinity whatsoever. So with this condition, we can be sure about that won't happen. All right. So that's the first version. And the second version is that, well, if we have an infinite series, this right here diverges if we can show that the series of an, this right here is greater than or equal to a series that you already know. That's actually a divergent. So the idea is that this, remember, a convergent means that you get a finite value. And yes, you can see if this is less than or equal to a finite value, that means this right here has to be also finite. Therefore, we can conclude that this right here also converges. And when we have a divergent, if you are talking about just positive terms, this right here, you can just think about it as positive infinity. Right here, you have something that's bigger than positive or positive infinity. Therefore, this right here has to be a bigger infinity, right? That kind of thing. So this right here has to diverge as well. And again, make sure that the terms are positive so we don't end up with negative infinities or whatsoever, all right? And then one more. Let's see if I can fit this right here. The last thing is the limit comparison test. Here, we are going to use two an and bn, right? So let's say here we have an, that's positive terms, and also bn, that's also positive terms. Right here, when we have limit comparison test, right here we will just say the series of an and the series of bn. I know there are a lot of things for us to write down, but we'll try our best, right? So this is the one that you are trying to work out. You're trying to determine if this right here converges or not. This right here is the one that you know much better, the easier version, things like that. So this is kind of like this or that, right? So the series of Bn. So you will have to try to simplify the series a little bit and end up with this, and then just use the P series or the geometry series to decide if it converges or not. You can draw connection between this and that. We will say this and that either, right? Again, either both converge or both diverge. I run out of space. I will just do like this. They both converge or they both diverge if you do the limit. Right, this is the limit, not the series. As n goes to infinity, you just do an over bn. Technically, the order right here doesn't matter, but usually we just put down an divided by bn. If this limit is finite, so we will put this down as less than infinity, and it cannot be 0. So this right here, it has to be a positive finite number. Then you can just draw a conclusion that either they both converge or they both diverge. And again, we will write that down because I just noticed that note. Let's just put on a little note right here. an and bn both greater than 0. All right? So, okay, I think this is pretty good. Here is the first one. It's always a good idea to write this down as a series. So let's see, n goes from 1 to infinity. And if you look at this 3, it's the same as 1 times 3. This 8 is the same as 2 times 4. And this right here is the same as 3 times 5. And this right here is the same as 4 times 6. So on, so on, so on. So if n starts with 1, well, this is just 2 more than that, right? So you can see that we just have n times n plus 2. So this right here is the series in the summation form, right? Just like this guy right here. This is my scary sigma picture. But anyway, though. So first, notice that for the bottom here, we have n times n plus 2. So we can just do partial fractions. And again, we can actually use telescoping series for this. So let's see. Let's do the telescoping right here real quick. So this is the telescoping approach. Well, I'm going to just write this down right here. This is the sum as n goes from 1 to infinity. And we have two denominators. And you know this is going to be blank over n plus blank over n plus 2. How do we figure out this? Well, do the cover up method. We go back to the original and cover this up. N shall be 0. And you put 0 in here. You get 1 over 0 plus 2, namely 1 over 2. So this is the number right here. And then to figure out this, well, we go back to the original, cover this up. N plus 2 shall be 0, so that means n shall be negative 2. You put that right here, so you get 1 over negative 2. So you get negative 1/2 right here. And now have a look. This right here, what we can do is, we have 1 over 2, 1 over 2, right? So we can factor that out. We can put it all the way in the front of the summation, just like how we do the integral. And then we will just have 1 over n, and this is a minus now, and then we have 1 over n plus 2. So as you can see, this is indeed a telescoping sum. Why? Because if you look at this as an, then you can see that this is precisely an plus 2. Right? Because they are just off by 2, right? So this is telescoping. And we are going to do it the quick way because I showed you guys the long way last time already. This is the quick way. Don't forget to put down the 1/2. So let's go ahead and put that down. Quick way, because they are off by 2. This is what we do. Starting at 1. You put it here, 1 over 1 is 1. And then you have to do it again. Next number is 2. You put it here, you get 1 over 2. And you just need 2 terms because again, they are off by 2. All right, good. Then we also need to look at this and then produce the last 2 terms. So we just have to write this down right here. That's minus 1 over n plus 2. And then we need another term because remember, 2 terms in the front, 2 terms at the end. The term before that is going to be still minus, and this is going to be 1 less than 2, which is going to be 1. So we have the 1 over n plus 1, just like that. So This is how we get the nth partial sum when you have a telescoping series. However, we still have to account for the infinity, and we just have to take the limit for that as n goes to infinity, right? Just like that. Okay, now you can see that when we take the limit, 1 over infinity is 0, likewise that. So this is pretty nice because this and that are just going to be zeros. And all in all, we just have to do 1 over 2 times 1 plus 1 over 2. This is 3/2 times 1/2. Altogether, we get 3 over 4. So, after all this, as you can see, we do end up with a finite value. Therefore, this right here, of course, converges. So perhaps I will put it down right here. Converges by telescoping method. There we go. Right? So that's that. Now, I would also like to show you guys the integral test. Yes, you can do the direct comparison for this, or maybe the limit comparison. But let me show you guys the integral test because I want to show you guys what we'll end up with for the improper integral. All right, applying the integral test. Firstly, we have to define the function. Well, our function is just going to be, you replace the n with x, so we have 1 over x times x plus 2, right? So that's the function. And usually, just go ahead and supply me a graph on the side and just look at when x is greater than 1. So if you look at this part, you will see the function will look like this. And just go ahead and mention that f is positive because it's above the x-axis, and it's also continuous, and also decreasing, right? And you also mention that this is true for x is greater than or equal to 1. We don't care about anything less than 1. So just go ahead and mention that. So that way we can legitimately use the integral test. All right, so to use the integral test, what we do is we just have to check the corresponding improper integral, namely the integral going from 1 to infinity, 1 over x times x plus 2 dx. All right? So to do this, in fact, it's pretty similar steps because we can just do the partial fraction. So this is the integral going from 1 to infinity, and we'll just look at that and put down x instead of n. So we have 1 over 2 over x, and then minus 1 over 2 over x plus 2. Partial fractions. And then integrate that, we have the 1/2, and then 1 over x is ln x, and we don't need the absolute value because we are going from positive 1 to positive infinity, so that's okay. And then minus 1/2, and then we have ln, and then we have the x plus 2. All right? Well, we don't need to put on the plus c, and we do have to plug in the numbers. When you plug in infinity though, we will technically end up with infinity minus infinity. So we are going to fix it a little bit. Notice that both of them have 1/2. So we will just write down the 1/2 one time. Both of them have the ln. This is subtraction, so we can just do x over that. Right? So we can just do that. And then we will plug in the numbers 1 and also infinity. When we plug in infinity though, that's actually a limit, so we will have to just do it on the side real quick. If you look at the limit as x goes to infinity, here we have 1/2 ln of x over x plus 2. This right here, it's the same as you put a limit inside, which is 1/2 ln, and then you have the limit as x approaching infinity of x over x plus 2. Right? How we can do that? Because natural log is a continuous function, and when you have the limit of the natural log, just go ahead and put the limit inside, do the things inside out, that kind of thing. And then when you do the limit as x goes to infinity of this guy, you can just do it the quick and easy way, namely pay attention to the highest power of x on the top and bottom, which is this and that's going to be just 1, and you just have 1/2 ln of 1. And yes, we did all the work for 0, but we didn't do all the work for nothing, right? We achieved something, which is we get a 0 for it. Anyway, so when we plug in infinity, the first term is going to give us 0, so I'll put that down in blue, all right? And if you are doing this for the test, of course, you just put this down somewhere so you can show work for that. And then we have to plug in 1 into here, and that's a minus. So it's minus 1/2 ln of 1 over 1 plus 2, which is 3, of course, but let me just write that down, right? Go ahead and fix this a little bit. This is just 0, and then you can put a negative right here. So this is 1 over 3, right? But when you have the negative for the exponent, you can write it as 3 over 1. So all this is going to be just 1/2 ln 3. Right? So just do that for that. All right, as you can see, because the improper integral right here does converge to 1/2 ln 3, so that means the infinite series also converges. So perhaps I'll write it down right here. You can also mention that this right here converges by the integral test, IT integral test. And just apply that. And the thing I want to mention is that, yes, we can just do the integral for this, but we get this for the value 1 over 2 ln 3. However, if you do add up all these numbers, the answer is actually 3 over 4. So the key is that when we have an infinite series versus its corresponding improper integral, we can only say either they both converge or they both diverge. We can almost never say they will converge to the same value, because that's not true. As you can see, this is 3 over 4, this is 1/2 ln 3, right? So I think that's rather interesting. Let's go ahead and write this down as an infinite series. Firstly, you can see that we have 1, and this is 2 squared, 3 squared, 4 squared, and so on. So of course, the top is just going to be n squared. So that's pretty good. Now, on the bottom, we have 2, 9, 28, and then 65. Have a look. This is the same as 1 to the third power plus 1, and this is 2 to the third power, which is 8, and then plus 1. And then 3 to the third power, which is 27 plus 1. That will give you that. And then 4 to the third power plus 1, it will give you 65. So my recommendation is that you should be familiar with perfect squares and also perfect cubes. And sometimes you just see that the numbers are like maybe 1 or 2 off from the perfect squares or the perfect cubes. In this case, we have n squared over n to the third power plus 1. So that's the formula for this. And for this right here, we can do 3 things again. We can actually use the improper integral test, just the integral test actually. Or we can use the direct comparison, or maybe the limit comparison. Earlier, I showed you guys the integral test already. So for this one, let me show you guys both comparison, right? So just to be fair. So right here, let's go ahead and do the direct comparison test. And this is how I usually show my students. First, remember this like the unknown convergent or divergent that we have to put down first. So that's the first step. You must know something so that you can compare this with whatever you know. And usually, the way that we can figure out the thing that we know that's easier and so is just pay attention to the highest power of n and highest power of n. So altogether, you can just see that it's this over that. Just ignore the 1. And when you do this, this is just like a little write out to just be slightly more formal in terms of give out the reason. All right, so we know that the series as n goes from 1 to infinity, n squared over n to the third power is just 1 over n, so we can simplify that real quick. And this right here, because the power here is 1, so let's just go ahead and put that down. Notice the p here is 1, which is less than or equal to 1. Therefore, by the p series, this right here diverges, right? And of course, you can be fancy a little bit. You can say this right here is the harmonic series that diverges as well. Of course, you can also say that. Now, the next thing that we'll do is we are going to check. If we are doing the direct comparison test, we have to check inequalities. So this is how we do it. put down the one that we are trying to do, which is the series as n goes from 1 to infinity, n squared over n to the third power plus 1. And we are going to see, well, this right here, because we have a divergence, remember, we have to show that this right here is greater than or equal to, but we don't know yet. We have to show that this right here is greater than or equal to a divergence that we know, which is the series as n goes from 1 to infinity, 1 over n. So you have to put down this inequality, because if this is true, that's the only case that we can continue and draw a conclusion, right? But I don't know if this is true yet, that's why I put down a question mark. So let's see if the direct comparison is going to help us out or not. Well, to show if this is greater than or equal to that, and notice everything's positive, we can just ignore the summation, we can just compare this and that. So we can look at n squared over n to the third power plus 1. Is this greater than or equal to 1 over n? Well, if this is not so clear, let's just go ahead and cross multiply. Everything's positive, so we don't have to flip the inequality symbol. N times n to the second power, we get n to the third power right there. Is this greater than or equal to this times that, which is n to the third power plus 1? This is upsetting. This right here is not true. So this right here is false. Of course, right? If it's not true, of course it's false. But anyway, the key right here is that if this inequality is false, that means we cannot continue. We don't get to draw a conclusion at all. So unfortunately, we just have to cross this out and then try again. All right? So we did use the direct comparison test. Unfortunately, the direct comparison test couldn't help us out because the inequality was not true. So we could not draw any conclusion, right? But don't worry, because we have another comparison test, namely the limit comparison test. So instead of doing the direct comparison test, let's try to use the limit comparison test. Guess what? The first step is the same. We are going to put down what we know, which is right here already. But instead of checking inequalities, we'll actually be checking limit. So here is the deal. Let's go ahead and put down the check right here. The check is, we will take the limit as n goes to infinity. And remember, an, right, is the one that we are trying to do, which is this right here. This whole thing is the an. And then the one that we know that's much easier, this right here is the bn. And we're just going to write down an over bn, which is n squared over n to the third power plus 1 over bn, which is 1 over n, like so. So go ahead and just do this limit. Well, let's multiply the bottom and the top by n, this and that cancel. So this right here is just the limit as n goes to infinity, n to the third power over n to the third power plus 1. As n goes to infinity, we just care about this and that. So this over that is just 1. So the answer right here is equal to 1. But this one, yes, it's the answer. You have to remember what's the condition for us to use this answer. You have to mention that 1 is greater than 0. This is finite and this is not 0. And congratulations, because this is the finite value, it's positive and it's not infinite, we can draw a conclusion with the limit comparison test. So let me just write down the conclusion right here. The conclusion is that the one that we are trying to do, which is the series as n goes from 1 to infinity, n squared over n to the third power plus 1. Let's use the word also, because the connection is that this right here is also divergent. If you put down the word also and just read it out loud, it will make sense. This series also diverge just like that. You cannot say this right here diverges and this right here also converge. That doesn't sound right. Check this out. I don't know if you guys are wearing a black shirt or not, But suppose I'm wearing a black shirt right now, and I tell you, hey, oh my God, you're also wearing a purple shirt. Does that make sense? I don't think so. Okay, let's write down a formula for this. The sum as n goes from, depends on how you want to write it. We can go from 2 to infinity. Why 2? Well, because 2. And also, have a look, this right here is what? 4, which is actually 2 square. 9 is the same as 3 square. This is 16, which is 4 square. So, the deal is that if we start with 2, then the formula is 1 over ln. The base is just n. But the power, again, if you look at 4, 9, 16, 25, they are just going to be n squared. So this right here might look super intimidating because we have n, and then to the n squared power. That's bizarre, but don't worry too much, because we can actually bring this to the front, right? Thanks to the ln property. So this right here is actually the same as the series as n goes from 2 to infinity, 1 over n squared in the front now, times ln n. So this right here is actually the series. What are we going to try? We're going to try the comparison. This time though, we are going to try the direct comparison. Notice that you have 2 candidates, 1 over n squared, and the other one is 1 over ln n. Just pick the dominating part. Usually that will work out very nicely. And by dominating part, you should remember the list. So let me just write it down for you guys. The list says as n goes to infinity, ln n is the smallest infinity that you will get, and the next is n to the p's power, and the next is b to the n's power, and the next is n factorial. So this right here is the smallest infinity, and this right here is going to be bigger. And by this right here, by the way, p has to be greater than 0, and b right here should be greater than 1. So here's the deal. Let's go ahead and use the direct comparison, dct right here. And again, let's go ahead and put down what we know. This time, we are going to be using the series as n goes from 2 to infinity. We can just match with the same index, right? The starting value doesn't really matter that much. As long as you have infinity right here, the p series, things like that, it will still work the same way. Anyway, 1 over n squared here, right? Again, just that right here. And you will see this guy is the p, which is 2, which is greater than 1. Therefore, this series converges, right? So that's what we know. Next, we are going to just do the check. And remember, we are doing the direct comparison test. So we have to do what? We have to do inequalities. So we are going to put this down, which is the series, as n goes from 2 to infinity, 1 over n squared ln n. We hope to show this is less than or equal to the series that we know, which is 2 to infinity, 1 over n squared. Now, here's the deal. Just lose the summation. We have 1 over n squared ln n. Is this less than or equal to 1 over n squared? Everything is positive. We can cross multiply real quick. Put this here, we get n squared. And then put that here, we get n squared times ln n, right? So now, here's the small trouble whenever this kind of things happen. So I don't really like this kind of thing sometimes whenever we run into it, but let me just take some time to explain it. When we put this down, we are supposed to say that, are we having this inequality to be true for n is greater than or equal to 2. Right? So that's what we are trying to do. So right here, we have n squared that's less than or equal to n squared ln n. You may see that this right here is bigger, right? Well, technically, but let's divide both sides by n squared. They cancel. You get 1 is less than or equal to ln n. Is this true when n is equal to 2? Not really. Yeah. So don't worry about that though. Here's the deal. This right here is not true when n is equal to 2. Right? If you put 2 in here, ln2 is 0.693 and so on. This is not true, right? But true for n is greater than or equal to 3. As long as it's true for some value, like n is greater than or equal to some value, then this is actually okay. So if the first number doesn't work, this right here is still okay. So that's one of the things that's like really hard to grasp. And usually I don't like to assign this kind of problem. I should have start with 1 over ln 3 to the 9th power, and then this, and then that, and so on, so on, so on. But if this kind of things happen, then you just have to remember that if the first number or the first two numbers are not true, that's actually okay. As long as this inequality is true for n that's greater than or equal to some number, that this is eventually true, then that's actually okay. So just keep that in mind. Anyway though, conclusion. And again, the key is true for this right here. Just keep that in mind, right? So we can draw a conclusion. The conclusion is that the series, as n goes from 2 to infinity, 1 over, let's put down this right here because it's the intimidating looking one. This right here also converges. Why? Because we did the direct comparison test by DCT, and we are done. Okay, so right here, the deal is that once you write this down in the summation form, and start with 2 again, okay? No problem on that. Well, I remember why I didn't want to start with 1, because the first root of 2, that doesn't look good at all. So anyway though, we have the nth root, right? So the first one is the 2, and then 3, 4, 5, and so on. And then the bottom, this is also n. So that's pretty much it. And we know in calculus, we almost always look at the radicals as power, right? Fractional power. So let's write this down as the sum as n goes from 2 to infinity. Look at this as 2 to the 1 over n's power over n, like so. All right? So for number 4 right here, let me tell you. For this, we can actually use both the direct comparison and also the limit comparison. I actually forgot to mention, for number 3 earlier, limit comparison wouldn't work because you end up with limit being equal to 0. But anyway though, yeah, too late for me to do that. But anyway, for this right here, limit comparison or the direct comparison, they will both work. Direct comparison is the one, okay. So, look at the sum as n goes from 1 to infinity. Which one are we going to choose though? Ignore this. Just look at 1 over n. Oops, it should be from 2, right? Yeah, just look at that. Just forget about that. 1 over n. Why? Because you actually get to show this is bigger than that. But anyway, let's just have the usual write out. This is 1. So the p here is 1, which is less than or equal to 1. Therefore, this thing right here diverges. Right? So this is what we know. Oh, I forgot to write down what we know. I want to have a consistent solution for you guys. So this is what we know. The sum as n goes from 1 to infinity, 1 over n. And this right here, the p is 1, which is less than or equal to 1. Therefore, it diverges. All right, now do the check. If we are doing the direct comparison, then the check is put this down, the series as n goes from 2 to infinity, 2 to the 1 over n's power over n. And because we have a divergence here, so we hope to show this is greater than or equal to, but we don't know yet. Put down a question mark right here. We hope to show this is greater than or equal to that. 1 over n. Well, oops, sorry. Take out the summation, look at 2 to the 1 over n, is this greater than or equal to 1 over n? Multiply n on both sides. Is 2 to the 1 over n greater than or equal to 1? Is this true or false? The answer to this is true. And one thing that you guys can do is that you can just use your graphing calculator if you're taking like a AP calculus class or maybe like a calculus class that allows you to use a calculator. Just go ahead and graph 2 to the 1 over x power. And right here, we just care about for n is greater than or equal to 2, right? So here is the deal right here. If you look at the graph for that, you will see this is 1, right? This right here is 1. This is 1. And you will see when n is equal to 1, you pretty much will just get 2. And then when n is equal to 2, you get square root of 2, which is that. And then you actually get this kind of picture. Right? And of course, if you graph this by the function, you could just connect the dots. But anyway, though, this right here is true. Yeah. So just supply a graph. Usually that's okay. Okay. And for my class, I won't ask you guys like some tricky question. I won't ask you guys, hey, the graph looks like this. But all of a sudden, the graph goes like that. I won't do that to you guys. That's the check. It works. So finally, here is the conclusion. And we'll just write this down. The sum as n goes from 1 every time 2 to infinity. Let's write that down because it looks nicer. This right here also diverges. Why? Diverge. We use that, right? So we'll just say by the direct comparison test. Yeah, just like that. Here we have the series as n goes from 3 to infinity, 1 over n times ln n square. All right? Let me tell you, direct comparison won't work. Limit comparison won't work. Because if you compare this with 1 over n, or the series of 1 over ln square, the inequality won't work out the way that you want it to be, and the limit, you'll end up with 0 or infinity, depending on how you put the an over b and things like that. So comparison tests won't work for this. So what do we do? First, let's imagine. If you have an integral, 1 over x, ln x, and then square, can we integrate that? The answer to that is yes. So we will do the integral test. This is one of the classic examples that direct comparison tests won't work, but the integral test will. So you have to give integral tests some love. You cannot say that I don't like improper integrals, so I will never use the improper integral test. You cannot say that. This is an example that you have to use the integral test. Anyway, write down the function, which is 1 over x ln x square, and then supply the graph real quick. I haven't used a calculator for this yet, but you know what? It's going to look like this almost always when you have a regular calculus 2 question that requires the integral test. Anyway, just write down f is continuous, decreasing, and positive for x is greater than or equal to 3. And then we can be legitimate and use the improper the integral test. All right, here's the check. Sorry for the bad handwriting. Here's the check. Check the integral going from 3, oh my goodness, every time. Going from 3 to infinity, 1 over x times ln x to the second power dx. All right, so for this right here, we can just let u equal to ln x, and you can see that du is just equal to 1 over x dx, and you can see dx is equal to x du. If you have been following me, then you know that I like to isolate the dx so that you can see the cancellation better. I know 1 over x dx is there already, but usually that's how I like to do it. Anyway, can we finish everything in the u world? Yes. So in that case, remember this is x going from 0 to infinity. So take these numbers to the u world as well. When x is 3, you put it here, so you will get u equal to ln 3. And then when you put infinity to here, ln infinity is infinity. So you will be infinity here. All right, then we have 1 over x, and this is the u, and we have the square, and the dx is that. And we can see the x cancel out very nicely. One of the most satisfying feeling in math is the cancellation, isn't it? All right, so integrate this. Again, we finish everything in the u world, so I'll just put on ln 3 and then infinity. Look at this as u to the negative 2, and this is du. Add 1 to the power, this is negative 1, so divided by that. So it looks like we have negative u to the negative 1 is just 1 over u like this. And then we are going from ln 3 to infinity, like so, right? You know what? I'll put it down here, yeah. Okay. And then plugging infinity, plugging ln 3. So first we get negative 1 over infinity. So that's the first term. And then we are going to minus negative 1 over ln 3. Like that. Congratulations. This one right here is 0. So this guy doesn't contribute anything. And then finally, negative negative is of course positive. So this right here is equal to 1 over ln 3. This improper integral converges to 1 over ln 3. So this right here of course converges. Thus, we can go by there and draw the conclusion that, so here is the conclusion. Our infinite series, 1 over n, ln n to the second power, this right here also converges. But we cannot say this converges to 1 over ln 3. We don't know. In fact, I don't know the value for this. I don't think you guys know either. I don't know if anybody can figure this out. But anyway, the only thing we can say is this infinite series also converges, and we can say that this is by the integral test, IT. Who doesn't love abbreviations? So that's it for that. We do see the 1 over n squared, but it's inside of the sign. Maybe there's a connection. So let's do some comparison. And I don't think the direct comparison will work out nicely because remember direct comparison we have to do inequalities, and when we have like sign, I don't really want to work with inequality when we have like sign trig functions and things like that. So let's try the limit comparison test. So limit comparison test in action. Let's go ahead and put down what we know. So from here, what do we know that's actually much easier? Well, if you look at the series as n goes from 1 to infinity, just look at 1 over n squared. We know that this right here, p is equal to 2, which is greater than 1, therefore it converges. So that's what we know, yeah? Now, limit comparison test, we are going to check the following. Again, for this one, maybe direct comparison test, the inequality, maybe it's not a good idea. So limit comparison test. Therefore, we check the limit. As n goes to infinity, put down this on the top, which is sine of 1 over n squared. And let me just do it like how I did it earlier. Remember, this thing is the an, and this thing here is the bn. So we put on an over bn. Sine of 1 over n squared over 1 over n squared, like so. Right? So this right here is a limit that we should work out. However though, if you put on infinity into here and here, sine of 1 over infinity is just sine of 0, which is 0. On the bottom, you also get 0. This is a 0 over 0 situation. But try not to use L'Hopital's rule for that, because this is precisely the limit. To do so, what we can do is let theta to be 1 over n squared. Check this out. As n goes to infinity, you put it here, then you can see that theta will go to 0. So if you take this limit to the theta world, this is the limit as theta going to 0. And then we just have sine of theta over the bottom is also theta, isn't it? And this right here is the famous the limit. And the answer for that is equal to 0. Factorial. Okay, I will stop. I'm sorry, it's just equal to 1. Alright, this right here is famously equal to 1. And in my class, once you have this, you don't have to show any other work. And I told my students I would really prefer, I would really be happy that if you don't do any L'Hopital's rule for that. But anyway though, this is 1. And you have to tell me that 1 is greater than 0 because remember when we are doing the limit comparison test, this right here has to be a positive finite value, which is. Therefore, we can actually draw a conclusion. We can be really happy. Conclusion, the one that we are trying to do, the series as n goes from 1 to infinity, sine of 1 over n squared. This right here also converges. How do we know? By the limit comparison test. That's it. It's actually not so bad because when you have the plus 4, just forget about it. Look at that, 2 to the n over 3 to the n. It's the same as 2 over 3 to the n. That should remind you of the geometric series, right? So let's go ahead and do that. And you have choice for this one. You can either use the limit comparison test or the direct comparison test. Both of them will work out very nicely. Let's do the direct comparison because we did a limit one earlier. So direct comparison test. Yeah, okay. So let's put down the one that we know. And for the one that we know, just go ahead and look at this and look at that. And again, when you write this kind of things down, it's just to be slightly proper to argue that this right here also converges or also diverges. Anyway, sum as n goes from 1 to infinity, this is 2 to the n over 3 to the n. But notice this is not p series anymore. Don't worry though, this is still nice. This is 1 to infinity, 2 over 3 to the n. Thus, we can say that here is the r, which is 2 over 3. But don't just tell me the r is 2 over 3. You will have to say that the absolute value of r is less than 1. Therefore, this geometric series converges. And when you put on r, people know that you are using the geometry series. Well, at least I know for my class. Because this is like the appetizer, not the main dish. The main dish is over there, so you don't have to say too much for that. But anyway, check. Direct comparison test, we will do the inequality. Put on the one that we are trying to do. So the series, as n goes from 1 to infinity, 2 to the n over 3 to the n plus 4. Is this less than or equal to the series as n goes from 1 to infinity, 2 to the n over 3 to the n? And notice that this terms and that term are positive, so just go ahead and do the usual thing. 2 to the n over 3 to the n plus 4. Is this less than or equal to 2 to the n over 3 to the n? I know this is true because the bottom right here is bigger, right? But yeah. Anyway, multiply, just do the usual thing if you like. So this is 2 to the n times 3 to the n. Is this less than or equal to 2 to the n times 3 to the n plus 4? This and that, they are never, it's not 0, so you can just cancel. 3 to the n less than or equal to 3 to the n plus 4. Is this true? I think right now it should be clear. This is definitely true. It is true for all n greater than or equal to 1. So anyway. Alright, so we can be happy. We can draw the conclusion. The conclusion is that the series that we are trying to do, 2 to the n over 3 to the n plus 4, also converges by the direct comparison test. Converge or diverge? Well, don't look at 1 over n, don't look at 1 over square root of n. This is not so bad at all because they are multiplying, right? So this right here, it's the same as the sum as n goes from 1 to infinity, 1 over n to the first power times n to the 1/2 power. Of course, we can just add the powers together. Therefore, we can see that this is just the sum as n goes from 1 to infinity, 1 over n to the 3/2 power. That's very nice. Why? Because we can look at this and we can say that, hey, the p is equal to 3 over 2. This right here is greater than 1. Again, don't just say p is equal to 3 over 2. You have to say 3 over 2 is greater than 1. Therefore, you know this right here converges. And because this is the only equation, we'll say by p series. And with that, we are done.